Okay, in this video, we're going to go ahead and finish section 1.2, graphs of equations. And there are two main topics to cover. Those are symmetry and circles. So here you have a definition. Go ahead and pause the video if needed and go ahead and copy it down first. So symmetry with respect to either the x-axis, the y-axis, or the origin means that if you fold along the Cartesian plane, so like your xy plane, along that line, so by line I'm referring to either the y-axis, okay, the x-axis, or the origin, okay? So if you fold along any of those three items or one of them at a time, okay, you will have a reflection of one side the same as the one on the other. So kind of like a mirror image. So here we have the three cases. Okay, and I'm going to move it up just a little bit right there. Okay, go ahead and copy that down as well. We have that with the x-axis. Okay, x-axis symmetry. That's this one right here. What happens is you're folding along this line here. So think of this if this were like a piece of paper, and if you wanted to fold it, everything on this side, so everything on this side would reflect over to this side. Okay. If this happens, if we have a graph that's like this, that looks like this would be considered x-axis symmetry. Now, algebraically, there's a way to prove this as well, and that is this right here. So if you can see this, I'm going to kind of move this just a little bit because I don't want to show you this bottom part quite yet. But if you can see this right here, our positive xy, if they're the same as this point down here, so if the y's line up on the same x, okay, then this means that you have x-axis symmetry. But this has to be true for every single xy that we have up here. So all of these points have to match up with a point that's down here. Okay, and we're going to go into a little bit more of this in a few more examples. With y-axis symmetry, we have a fold over the y-axis. So now you're thinking a vertical fold, okay? And everything on this side, the right side, is reflected over to the left side, okay? If this happens, you can see that the x value is the one that changes this time. So the x value is negative here and it's positive here, but the y values will be the same. So unlike the x-axis symmetry, so here in this one, our y's were the ones that were different, okay? So just how I have it here, up here, I went ahead and wrote it down here as well, but I also included the notation. So if both my x and y are positive on the other side of the y-axis, your x will be negative and your y will still be positive. So that's just the flip that you see here, okay? And finally, we have origin symmetry. So this one is a little bit different, or a lot a bit different, I should say. What happens with this one is we start off with the point, okay? And it's kind of messy on this one, but this is x, y, okay? And it flips and it flips. So you could think of it like it flips over the origin. So there is this, and actually I made something here. I'm gonna try to see if it'll work. So think of it like this one, okay? Like this graph that I drew on this paper. This is a perfect square, or as perfect as a square as I could make it. And what I did is I just folded it in half. And actually, let's make this even better. Let me go ahead and put like a blank screen here so you can see what I'm talking about. Okay. So what I did with this square is I folded it in half and I folded it in half again, and that gave me my x and y axis. Okay, then I went ahead and folded it diagonally each way. Okay, and this gives me the cross section that I want for the origin symmetry. Okay, so hopefully this works. If you were to think of the shape that we had up here, so let's say we have this piece right here, okay? If I do this dark enough, okay, and I tried to do it pretty dark, and you fold it over this axis, so over the diagonal here, okay? And I'm just gonna press it down as hard as I can to make it flip over onto the other side. Okay, so you can kind of see it's really, really light, but it kind of did this. Okay, so now I'm going to darken that piece. Hopefully I don't tear the paper. So now it's right here. Okay, and then I'm going to go ahead and flip this piece over this line. So it's like a double flip. You flip and then you flip. So let me erase the first one that I had just to make it lighter. Like I said, this usually works better with if you have like paint or something, but all I have is pencil, so that's what we're going to work with. So now I flipped it over this way. Okay, I'm going to flip it over this way now. Do the same thing. Maybe that would help. I don't know. We're experimenting here. Okay, and you can kind of see it's really, really light. You can kind of see that it kind of did this. Okay, so going back to the original figure, so now I'm going to erase the one that I first did here. Okay, and I know it's super messy. The original figure was this one, the one that I erased a few seconds ago. And you can see that this figure is exactly what I had on that last graph. And that's how origin symmetry works. It's a double flip. You flip and then you flip again, and you have everything in this quadrant double flipped over to this quadrant. So what happens is this xy, okay, is now negative x, negative y, because we flipped it over 2 times to change this entire space into the one over here. Okay, so hopefully that's a little bit of a visual, and you can do this with any figure. Like I said, it works better if you have a darker pencil, I suppose. But anyway, back to this. So that's what we have going on here. Okay, so just like I mentioned in the little picture you saw right now, this positive x and y is just negative. And if these are the same, if they equal each other for every single x and y, then this is going to be origin symmetry. Okay? Now, this thing that I'm talking about equaling each other, this is the algebraic process I'm going to show you, and that's going to happen in a few examples. Okay. All right. So let's go ahead and start with an example. This is example number 6. It says y equals x squared minus 1. What kind of symmetry? And I went ahead and put here in parentheses, this is just graphically. So we're going to start off with something kind of easy. We know that this is a parabola. Okay, you do have to know a little bit of background here. And the minus 1 just means that it's going to start at negative 1. So this graph, here we go. This graph has a y-intercept at negative 1. Okay, and then it kind of just goes up like this. You're going to have to trust me on this. If we wanted a better sketch, we would make a table just like we've been doing in the other previous examples or videos before. But the graph does look like this, and it mirrors the points on every side. So in other words, every y value is going to be the same as its x, positive x and negative x here. So this looks like to me, if I were going to try to fold it somehow, it looks like this is where my axis of symmetry, so to speak, would be, right? And since the axis of symmetry here is down the y-axis, well, this would just be y-axis symmetry. Now, if you don't know how to graph something like this because you just don't remember, this is where your graphing tools would come into play. Again, I do recommend you try doing the table first, but this is where you can use either the Wabbit Emu app or Desmos. And I can show you one of those in a separate video if you need. I do have the app on my phone. Actually, I can show it to you really quickly just so you can see what it looks like. Let me find it real quick. So this is the Wabbit Emu calculator. It looks like an old-fashioned calculator. And we could actually use this to graph something like this. So we could say x squared minus 1. Okay, there it is. We graph it, and there it is, just similar to what I just had on my paper. We can get the table. And if you see the table values here, okay, I'm gonna not go too far down. Let's go right there. You look at the table values here, you can see that all of my x's, so -3 and +3 have the same y value. -2 and +2 have the same y value. -1 and +1 have the same y value. So this is the kind of symmetry that we're talking about. Okay. If you still don't have this, let me know if you have questions on how to download it. Okay. The app is Rapid Emu on your Play Store or Apple Store. All right. So moving on. So that is symmetry graphically. Now we're going to go ahead and look at how to find the symmetry algebraically. Okay, so this is testing for symmetry algebraically. And what I did on this page is, don't worry about that yet. I went ahead and put testing for X, testing for Y, and then testing for origin. So go ahead and make sure you have all that first and our example. Okay, we're going to start with testing for the X axis. So as a side note here, remember that this is what we had on the other page, that our x and y have to be the same as our x and negative y values for every x and y on that graph. So what we're going to do is first, we're going to write the equation. So we're going to go ahead and do, ignore that, y equals 2x cubed. Okay. And what I'm going to do is I'm going to replace every, since these two are the ones that are supposed to be the same, okay, I'm going to replace y. So I'm going to replace this y with negative y. Okay, so my new function is going to be negative y equals 2x cubed. Okay, and the goal is to see if this is equal to the original. So if I can manipulate this function to look like, so if I can manipulate this to look this part to look like this part, then we are good to go. But remember that actually the entire thing, not just that. Remember that we have a negative here. So what I'm going to do is I'm going to see if I can work that out. Well, if I divide this by -1 and that by -1, I get y equals 2 divided by -1 is -2x cubed. So this is my end product. And if I compare these two, okay, they are not the same. So they are not the same. So that means that this one is not going to be x-axis symmetry. So it's not x-axis symmetry. Okay, let's try out for the y. So I'm going to move over now and I'm going to look at the y test here. Okay, let me focus this a bit. It seems like it's getting a little blurry. All right, so for the y-axis, we're going to be replacing the x, because remember the y's are the ones that stay the same, and these are the ones that change. So here's my original equation again, y equals 2x cubed. Okay, and for this one, we're going to replace the x. So replace x with whatever's over here, so negative x. Okay, so now this is going to look like so. Y equals 2. I'm going to put this in parentheses because I'm replacing this part right here. Okay, now this you got to be careful with, because if you don't remember your rules of powers and negatives and all that, you might want to expand this. So this would be 2 times negative x, negative x, negative x, because there's 3 of them. Okay, so when you have 3 negatives, that ends up with a negative. So this is going to be negative 2x cubed. Okay, I'm just going to bring down my y. And this is my end product on this one. So if I compare to the original again, we can see that they are not the same either. So not the same. It's the same as what I got over here, but that doesn't matter because I'm comparing to my original equation here. Okay, so that means that this is not y-axis symmetry either. Okay, so hopefully it's origin symmetry. And if it isn't, well, that's okay because believe it or not, there are more functions that have no symmetry at all. Okay, but let's see. So we have our test for origin now. So this one I put a whole bunch of space for because it's the one that kind of has the most work. For this one, you want to replace both of them because x now becomes negative x and y becomes negative y. So I'm going to start with my original equation. So y equals 2x cubed. And we're going to replace both. Replace both x and y, okay, with negative x and negative y respectively. And that word respectively just means I'm going to replace this negative x with the first one, negative y with the second one. They kind of match up each other. Okay, so let's go ahead and do that. Let's go ahead and do, instead of y, I'm going to do negative y. I'm going to equal that to 2 times. In the parentheses, I have negative x because I'm replacing it with negative x. Okay, so there's my negative x to the third power. Okay, so this kind of combines the two that we've already seen. So what I'm going to do is I'm going to expand the right side. So this is negative x, negative x, negative x. I'm going to leave this as negative y. I'm just bringing down that negative y for now. And I already know from my y-axis symmetry that this right here is going to give me negative 2x cubed. Okay, so now I have negative y equals negative 2x cubed. I can go ahead and divide by negative 1 to get rid of that negative here, which gives me y equals what happens here. We have another negative getting canceled out, so to speak, okay, because it's just equal to 1. And I'm left with 2x cubed. Is this the same as this? It is. This is the same. So that means that this one, it would be a yes, does have origin symmetry. To kind of go a little more in depth on that, if you noticed or if you remembered from a previous example, I believe, this is a cubic function. Okay, and cubic functions tend to have this shape, okay, which is really similar to what we already saw in that previous example with the origin symmetry. Okay, yeah, so there we go. Let's move on. We are almost done with this topic. And then we have to finish up with circles, okay? So last example for symmetry, and I'm just doing this one kind of as an extra because you will have a question like this. It says use symmetry, make sure you copy this down first. Use symmetry to sketch the rest of the graph. So we have 3 different cases going on here. We have x-axis symmetry with this shape, which means it has to reflect over this. Okay, so if I were to flip this over, well, I would just complete the puzzle. So kind of like this. Hopefully yours is straighter than mine is, but it's just finishing the curve. That's it. Easy. Y-axis symmetry, so that's going to be a flip over this line right here. So I just have to match up what I have here. If you're not that great of an artist, don't worry about it. I'm not doing that great here either. So there we go, done with that. And finally, we have origin symmetry. So origin symmetry, remember, it's that double flip where you flip over kind of this line and over this line, right through the origin. Okay, you could also think of it as a 180-degree rotation. Now, this is a tricky one because if you flip this piece over this line, well, it lands right on top of itself. So this piece right here, so this side lands right on top of this side, and this side lands right on top of this side. So they happen to land right on top of each other, which means the first flip is done. So we don't have to worry about that one. Now we just got to take this piece and flip it over this way. So that means we're going to have something kind of like this. And maybe you recognize this function. It's a rational function, 1 over x, which we will also see in the near future. Yeah, there we go. Done. Last topic. So this was the last example for this topic. Now we have the last topic. So ignore that scribble. Go ahead and copy all this down. You have a bit of information here on circles. Okay. We have that a circle is a set of points x, y in a plane that are the same distance r, so this is r for radius, from a point called the center, hk. And this is shown by the following equation. So let me kind of try to get this on the screen for you here. We have this equation, okay? R is equal to the square root of x minus h squared plus y minus k squared. And this should look familiar to you. This should look really similar to our distance formula. And it actually does come from that same formula because believe it or not, you can construct a whole bunch of right triangles inside a unit circle. Hopefully you remember that from maybe sometime in geometry. If not, it's okay. We'll look at it later. So what we're going to do is we're going to write this in standard form because this is not standard form for a circle. Believe it or not, standard form for a circle has a bunch of squares in it. So go ahead and write this down, standard form of a circle. And my device is moving all over the place. Standard form of a circle, okay? And standard form of a circle, what we're going to do is we're going to get rid of the square root. So to get rid of the square root, we're going to square both sides. So we're going to square both sides. Okay, and that's going to leave us with r squared. Okay, so I squared this, so now I have r squared is equal to x minus h squared plus y minus k squared. So essentially all I really did was I got rid of the square root and I left everything else and I made this into a square. But this right here is key because from here we can figure out a whole bunch of things from here. Okay, so I'm going to go ahead and move on to the next page because it's a little crowded on this one. There's some more information for you to copy there. We're almost done, guys. Circles are not that hard at all. So here at the top, okay, go ahead and copy this down first. Let me adjust this. All right, that should, there we go. So we have some information at the top. Go ahead and copy that down first. This is our standard form of a circle again. And all I did is I went ahead and just rewrote it in this format because this is how most problems will look. You'll have the x and the y on the left side and the r square on the right side. So we have this, I guess, just a note, a point xy lies on a circle of radius r and center hk if and only if, so this is important, okay? This point is only on the circle if this is true. So in other words, this has to be, this square plus this square has to equal to this square. And that comes from the Pythagorean theorem. Remember how I mentioned we could do right triangles in a circle. So this is kind of like your A, and this is like your B, and this is like your C, okay? Anyway, from this standard equation, we can get several things. We can get the center of the circle by looking at these two numbers, h and k, and we can get the radius by taking the square root of all this. So the square root of r squared is just equal to r, okay? Be careful here because I know in the past you might have been told that these were the opposite. Well, the reason they're the opposite is because we always have that minus in here. So, well, you'll see when we do an example, and I'll elaborate more there. So just to kind of show a diagram here, let's pretend that this is our circle, and we have our point in the middle, HK. Okay. And then we have a circle. Hopefully I can draw it somewhat straight, or not straight, but somewhat resembling a circle. Well, that's like a lopsided egg. That's all right. So anyway, the distance from here to here, this would be our radius, okay, or R. And then this point right here on the circle, this is our X and Y. So obviously, we can kind of put a little dash sign if you want. So obviously there are an infinite amount of radii, right? Plural for radius. So if I did another one, you don't have to do this part, but if I did another one here, I could find another point here, and that could be, I don't know, x2, y2. But the idea is that all of these points are equidistant from the circle here, I'm sorry, from the center here at HK, okay? All right, let's do an example of one of these problems so you can see how we're going to apply this. This is the last example, hang in there. Example number 9, okay? Go ahead and write this down. We have that the point 1, -2 lies on a circle whose center is at -3, -5. So they're telling us straight out that this is a circle, and this point is on the edge of the circle, and the center is -3, -5. Write the standard form of the equation of the circle. So what I'm going to first do is I'm going to rewrite that equation. Remember that that equation is x minus h squared plus y minus k squared is equal to r squared. Okay, you can color code it if you'd like. I'm going to do that just super fast. Okay, and what I'm going to do is, well, I don't really know where this, I don't know too much, but I do know that they gave me some points here, so I'm going to see what I can label. But it tells me the center is at -3, -5. And up here at the top, we wrote that the center is HK. So that means that these numbers have to go in here. So this is going to be my, let's see, this is going to be my H, and this is going to be my K. And just like in the diagram that we drew on top, we know that X and Y have to be on the edge. So, and it tells us this point is on the circle. So this is X and this is a Y up here also. So we're going to plug everything in and see if that helps us. Okay, so let's start off with that. So we have our X is going to be 1 minus our H is -3. So I'm going to go ahead and put that -3 right there. Okay, be careful here because remember there is a minus. So minus, just copy it down, -3. Then we have our y value. So our y is -2. Again, minus the k value. And our k value is -5. And this is all squared. Okay. And we don't have, let me see, we don't have r squared. So it looks like that's what we're going to be looking for to be able to figure out the rest of this equation. So this is all equal to r squared. So when you see what you're missing, you can see, okay, so that's the variable that I need to find so I can plug it back into the standard form. So at the end, I'm going to want it to look something like this, okay? But for me to have that, I need that R, okay? So I'm going to find that R. So from right here, I'm just going to go ahead and use PEMDAS. I'm going to bring it down a little bit because it looks a little messy to me. So using order of operations, we look at the inside first. These two negatives in both spots are going to make that into a plus. So I'm going to have 1 plus 3 square plus -2 plus 5 square is equal to r squared. Okay. Continuing my order of operations, 1 plus 3 is 4. So 4 squared plus 3 squared equals, again, r squared. 4 squared is 16. I'm running out of space here. Plus 3 squared is 9. And again, that's equal to r squared. 16 plus 9 is 25. And we could actually stop here if we wanted, because if you look at the formula is asking us for r squared. But just for the heck of it, let's go ahead and just calculate our r. So square root of 25 means that r is equal to 5. So our radius is 5. Okay. Now, before I go back into the actual equation, let me just kind of show you what I was talking about earlier about opposites and all that. So when you talk about centers and vertex and all that, we have told you, oh, just think of it as the opposite. This is why it's the opposite. So if you keep this minus in your formula, no matter what, so those minuses right there, if you keep them in there, when you plug in your values, so these values appear once right here. So if you once you plug these in and you combine it with that negative, this minus, that will automatically change the sign. I mean, think about it. If you have a negative and a positive, it's going to turn into a negative. Negative and a negative is going to turn into a positive. And that's what happened here. That -3 became +3, and the -5 became, so there we go, +5. If you're not sure, just, plug it in, work it out. Okay. So finally, we're going to just give our equation. So the equation looks like it's going to be x, okay, plus 3 square. And we're doing plus 3 because, well, I'm getting this from kind of like from here, okay? We're doing plus 3 because if you put two minuses, that doesn't look simplified. So we're going to do plus 3 plus y plus 5. And again, I'm looking at kind of like this piece right here, okay? This piece right here. Square is equal to r squared is 25. And that's it. You want a couple hints for this? Not hints, I guess tips. Remember the vertex? I'm sorry, the center. It's late, guys. I'm getting tired. The center is going to come from here. It's the opposite signs because once you plug it in, that minus changes it, and your radius is what we found here at the end. If you guys have any questions, as always, let me know. Send me an email. Thank you very much.